There is a number hiding inside geometry, inside nature, and even inside the counting numbers. Most people have heard of it, almost no one have really met it. I'm Saba and welcome to Hidden Math.
One of the most fascinating numbers in all of mathematics is the golden ratio. In this video, we're going to explore what the golden ratio really is, where it comes from, and how it appears again and again throughout mathematics. The golden ratio is defined using a special rectangle called a golden rectangle. If we remove a square from this rectangle, the smaller rectangle that remains has exactly the same proportions as the original. This unique self-similar property defines the golden ratio. Algebraically, if a line segment is divided into two parts, called A and B, in such a way that a divided by B is equal to a plus B divided by A, then this common ratio is called the golden ratio, and it is usually denoted by the Greek letter phi. History and pentagons. It is often claimed that the golden ratio appears in ancient Greek architecture and famous works of art. However, many of these claims remain controversial and are not always supported by precise measurements. What we do know for sure is that the Greeks encountered this ratio naturally in geometry, especially when studying the regular pentagon. If the side of a regular pentagon is taken as 1, then its shortest diagonal has a length equal to the golden ratio. Closely related to the pentagon is the pentagram, the 5-pointed star. If the smallest segments of this star are set to length 1, the larger segments turn out to be powers of the golden ratio. Renaissance and art. About 500 years ago, the Renaissance mathematician and philosopher Luca Pacioli became fascinated by this ratio and wrote a book called De Divina Proportione, illustrated by his friend Leonardo da Vinci. The book studied geometric solids, human proportions, and the possible appearance of the golden ratio in art and architecture. Some artists have used it explicitly. For example, Salvador Dali designed the Sacrament of the Last Supper using a golden rectangle. And the windows behind Jesus form a regular dodecahedron, a solid deeply connected to the number 5 and the golden ratio. But in this video, I don't want to judge whether the golden ratio truly appears in nature or art. Instead, I want to show you something much more solid: how the golden ratio emerges inside mathematics itself. Solving for phi. So, the golden ratio is equal to this number. Now let's see where this number actually comes from. Starting from the defining relationship, we say that a divided by b is equal to a plus b divided by a. From this, we can derive a quadratic equation, and solving that equation gives this exact value for the golden ratio. 1 plus the square root of 5, all divided by 2. The appearance of square root of 5 is not accidental. It reflects the deep connection between the golden ratio and 5-fold symmetry, pentagons, pentagrams, and regular geometric solids. In fact, this is why the golden ratio can even be written using trigonometric expressions involving angles of 36 degrees and 72 degrees. Fibonacci and Lucas numbers. Today, most people first meet the golden ratio through the Fibonacci sequence. As we take ratios of consecutive Fibonacci numbers, these ratios get closer and closer to PHE. But Fibonacci numbers are not alone. The Lucas sequence, named after Edward Lucas, starts with 1 and 3, and each new term is again the sum of the previous two. The ratios of Lucas numbers also converge to the golden ratio. but in a slightly different and more subtle way. Both Fibonacci and Lucas numbers can be written using powers of the golden ratio. These are known as Binet-type formulas, and they show something remarkable. Powers of the golden ratio, with or without division by the square root of 5, lie astonishingly close to whole numbers. Geometric constructions. Now let's return to geometry. A golden rectangle can be subdivided again and again into squares whose side lengths follow the golden ratio. From these squares, people often draw the famous golden spiral, though it is really an approximation, not a true logarithmic spiral. But the deeper question is, can we construct the golden ratio using geometry alone? There are many ways. Using only squares and a circle, here is one beautiful method. We start with 4 squares placed next to each other, one by one. Then we connect these 2 corners in the image. Now we draw a circle using this segment as the diameter. The length of this new red segment is exactly equal to the number phi, the golden ratio. But this is not the only way. Let me show you another construction. This time we use 2 squares and a circle. There is also a construction using 3 squares and a circle. And even another variation, again with 3 squares and a circle arranged differently. There is also a beautiful way to obtain the number phi using 2 regular shapes, constructed like this. The golden ratio also appears naturally in special shapes called kites and darts. When these shapes are placed next to each other in the right way, they create the famous Penrose pattern, or Penrose tiling. And even in 3-dimensional space, the golden ratio continues to appear. By arranging 3 vertical golden rectangles, each built from 12 squares, we can create a 3-dimensional form that looks like this. This is another way of making the number phi, purely from geometry. Continued fractions. Now, let's examine the relationship between the golden ratio and numbers. Look at these nested fractions. If we stop at any finite stage, the result is a ratio of Fibonacci numbers. But if we continue this process forever, the value approaches phi, the golden ratio. There is also another way to see this, without referring to Fibonacci numbers at all. We can label this entire continued fraction by the letter x. Notice that this red box is now x. Now we can write an equation for x, solve it, and show directly that x is equal to phi. And now, instead of nested fractions, we replace them with nested square roots. Once again, notice that the red box is equal to x. And once again, when we solve the equation, the golden ratio appears. Phi hidden among integers. Now for something more mysterious, consider the greatest integer function. This is the operation that takes any real number and returns the largest integer less than or equal to it. By inserting multiples of special irrational numbers into this function, we can generate 2 complementary sequences of integers. Using square root of 2 gives one famous example. But when we repeat this process using the golden ratio, something extraordinary happens. The positive integers split perfectly into 2 interlocking sequences. One sequence is generated by multiples of the golden ratio, and the other is generated by multiples of the square of the golden ratio. This is a special case of Beatty's theorem. The golden ratio is literally hiding inside the counting numbers. Final formula. Finally, we arrive at one of my favorite formulas. An infinite series involving powers of the golden ratio turns out to be equal to a continued fraction built from powers of 2. And when you write out the coefficients carefully, you see them, the Fibonacci numbers. To me, this formula is so unexpected and so perfectly structured that it almost feels humorous. mathematics smiling at itself.
Maybe the golden ratio is not hiding in the world. Maybe the world is hiding in the golden ratio. If you enjoy this journey, subscribe to Hidden Math.